about a few things. We'll talk about this quiz. We'll talk about the final exam. We'll talk about a few new topics here. Okay. So, first of all, next week is your final exam. Okay. The final exam is going to be, you will have 3 hours to complete the final exam. It should not take 3 hours to complete the final exam. It will be all multiple choice questions, about 50 to 55 questions long. I will provide Scantron form to you. You are allowed to have a note sheet with writing on the front and back. The final exam will have a heavy emphasis on chapters 7, 8, and 9. And a few questions from what I will cover today on sampling methods. And then there will be about 10 questions that are conceptual questions from before the midterm exam. I hope you guys took a look at the practice final exam and tried that out. I'm sorry?
Oh, it wasn't multiple choice. It was free response, right?
The practice final exam was free response, but the final exam will be similar to the practice final exam, except for each question you will have answer choices to select from.
That's still on the website, right?
This is on the website, on the page that says about the final.
Are those handouts for us?
These are not handouts, this is my copy. Part of your homework was to work on the practice final exam. We have a question?
Are we going to go over how to solve this practice?
Yes, I will spend some time today going over the practice final exam. Yes?
Did you say multiple choice only?
Multiple choice only, that's correct.
Are you going to have extra credits like last time?
If you score all 50 questions correct, you will have over 100%. So, yeah, I believe, yeah, either bonus questions or something. Okay. Regarding the quiz that you took today, I glanced through what was turned in, and to be frank, I'm a little nervous for you guys. I feel, or on those questions that were on today's quiz were taken directly from the homework section of your book. Okay, on the homework page that you did for last week, I said, be sure to know how to do, for example, I don't know. Let's say I said, be sure to know how to do chapter 8, problem 35 or something. And I used question 836 as the question for the quiz. Okay, so, and I maybe just changed a couple numbers, but if you could do 35, you should be able to do 36, but looking at some of the responses I got on the quiz, I'm not confident that everybody can do their homework on their own. Yes?
I have quiz B, and the first question I think is the exact same one as like 8:45 in the homework.
That's probably correct.
But I was doing that in the homework or whatever, and then I looked on your page, and you never put up a video how to describe it, so I never really learned how to do it, and I was wondering if you could write up the example. There's no answer for it on the page.
Was there a handwritten answer?
Nothing. It was a comma.
Okay, well. I might not have put up a video solution, but I'm thinking based on the other questions, you should have been able to answer. But we'll go over the quiz right now. Okay?
Wait, what number did you say it was? 835?
I don't remember. Okay? I don't know the exact numbers of all of these homework problems, you guys. But I do know that my question was based very much on the homework problem. So we'll go from there. Alright, so let's... Okay, so I changed the numbers between versions A and B that you use. So I'm just going to use some of these problems here.
Which version is that? Is that version B?
This one says version A, but it's all the same. Okay, so number one, it says a recently published article reported the results of an experiment on reducing the likelihood of men developing prostate cancer.
Yeah, that one I was like.
Okay, so this is the same as Chapter 8, Problem 50. Okay, and all I have done is change some of the numbers that appear in this problem. So it says the investigators randomly assigned 3,305 men to receive the drug.
Cancer drug.
The cancer drug, exactly. Okay. So, people who received the drug, there was 3,305 men. Okay. And then assigned to the placebo, we have 3,424 men. Okay. Of those receiving the drug, 659 developed cancer. And of those receiving the placebo, 858 had cancer. And so we wanted to, it says a recently published article reported the results of an experiment on reducing the likelihood of men developing prostate cancer. Okay, so in this case, what would the appropriate hypotheses be?
The appropriate one.
The hypotheses for this problem.
Would be P1 is equal to P2.
So the null hypothesis is that P1 is equal to P2. Alright? How do I know I'm using P's?
You're looking for
Because
proportion.
we're given, there's no standard deviation or mean.
Right, so when you read the problem, no mean, no standard deviation is given. You're dealing with a categorical variable. Did someone develop cancer or no cancer? So we have a categorical variable. And how many samples do we have? We have 2 samples. So our hypothesis test, our null hypothesis, starts off with P1 equal to P2. And that means the proportion of those who take the drug who get cancer is the same as the proportion of those who take the placebo and develop cancer. The null hypothesis says that whether you take the drug or the placebo, the probability or proportion that someone develops cancer is the same for both groups. The alternative hypothesis
P1 is less than.
would be what?
P1 is less than.
That P1, if P1 corresponds to the drug group, okay, so this will be, if we call the drug group Group 1 and the placebo group Group 2, we expect the proportion for Group 1 to be smaller than the proportion for Group 2. So these would be the hypotheses that we would use in this problem. Okay. Less than because we expect fewer people to have cancer if they take the drug. Yes, we have a question.
Why would it be P1 is less than P2 and not P1 is not equal?
Because the question says, a recently published article reported the results of an experiment on reducing the likelihood of men developing prostate cancer. So the idea is we're giving people drugs to see if it reduces their chance of developing prostate cancer. We do not want to make a drug that increases someone's likelihood of prostate cancer. So we want to see if the drug reduces cancer, and therefore, for the group taking the drug, what we're hoping to see is that the proportion that develop cancer is lower than for the group taking the placebo. Okay, so my null hypothesis is P1 is equal to P2. The null hypothesis always has an equal sign. And the alternative hypothesis is that P1 is less than P2. Okay, is that clear?
Is this the same for quiz B?
Quiz B is almost exactly the same. All I've done is change the numbers.
Oh.
Okay. Okay, part B says, what are the observed proportions of each sample? So the observed proportions, all that is asking for is what is p hat 1 and what is p hat 2. Okay, so p hat 1 is that 659 out of 3305 developed cancer. Alright, it's a little embarrassing. I'll have to break my own rule and use a cell phone as my calculator.
Bonus points.
Borrow my.
And this is going to make my life much harder.
0.19.
What is it?
0.19.
0.19? Okay. I don't know, just another decimal point. 0.199. So it's not 0.19.
What's
It's,
the point 0?
okay, 0.20 is acceptable. Proportion 2 is going to be 858 divided by 3424. Point, right, 0.251. So that is B. Okay, these are just the observed proportions. Please be quiet. Okay, for C, we are going to make the standard error. The standard error has this formula. P hat times 1 minus P hat times 1 over N1 plus 1 over N2. What is P hat equal to?
659 plus 858 over 305. Yeah. 3,000.
Yes.
You're tricky guy.
So P hat is equal to the total success. Success is arbitrary, is an arbitrary label, so divided by the total observed. So maybe it's not nice to call those who developed cancer a success, but that is the arbitrary label that we apply to the group. So we put 659 plus 858. This is the total number of people who developed cancer divided by the total number of people we observed. 3305 plus 3424.
.22544.
So I have 1517 up top divided by 6729 on the bottom. So that is 225. So my standard error is going to be the square root of 0.225. I'm just going to round off into 0.225. 1 over N1, 5 plus 1 over 3, 4, 2, 4. This is 225 times 0.
Do you want to borrow my calculator?
That would probably be helpful. Yeah. What's that?
On your final, like, would you give us like a problem like this, and then like for 5 questions, it'd be like, what's the standard error, what's the test statistic, what's that, and so on.
Yeah, it will be broken up similar to this.
So like 5, like around like 4 or 5 problems just for one actual.
Yes.
Okay.
Yes. All right. It's gonna be tough. All right, so I'm getting 0.0102 ish. So my standard error is in the vicinity of 0.0102. Maybe you're not getting something exactly that. Okay, the next question asks, what is the value of the test statistic? Our test statistic would be P1 hat minus P2 hat divided by the standard error. Okay, so your answer will probably be maybe a little bit different. It's not very precise. I have a z-score of negative 5.1. Okay. The fact being that the z is very negative. We know that the z-score represents how many standard deviations we are away from the mean. And so this tells me that I'm over 5 standard deviations away from the mean. So that is something very unusual. In fact, when I go to the z-table to see what is the area beyond 5 standard deviations, it is not on the chart. Okay, so the value of the test statistic is somewhere around -5 for part D. E asks, what is the p-value? Okay. So in our case, we have a one-tailed test. And so I don't need to do any kind of doubling. And I can look up on the z-table, it goes as far as -5, but basically my p-value is almost 0. If you write the p-value is equal or is less than This is also acceptable. But the p-value is almost 0. Yes.
So, for example, that number right there is for exactly negative 5.0.
Yes.
So, for example, on our test, version B, we got like negative 5.2 something,
Yeah.
right? And we could use an exact value that I calculated on the calculator, and I could have put that one down, right?
Okay.
Is that fine?
That's fine.
Alright, that's fine.
Is your value almost 0?
It was 2.22 times 10 to the negative 8.
Alright. That's good. Alright. What is the p-value of this test? P-value is almost 0. Okay. So part F, is that okay? That I'm just writing the p-value is almost 0. Part F says, based on the p-value, would we reject or not reject the null hypothesis?
We will react.
We would reject the null hypothesis. So anytime you have a small p-value, you reject the null hypothesis. In part G, what does this conclusion mean? This means what?
We have evidence
We have evidence
that the drug did not reduce
that the drug does reduce the proportion of men developing prostate cancer. Yes, we have a question.
Can you explain part G? How do you bring that up? How do you come up with that?
How do I come up with this?
Yeah.
So part F, we rejected the null hypothesis. That's correct, right?
Okay.
What were the original hypotheses that we made?
P1 equals to P2.
So no difference. Oh,
So on
no,
the,
they're the same thing.
so the original hypothesis was that P1 is equal to P2. Notice that there are no hats on my P's in the hypothesis. And the alternative is that P1 is less than P2. So that is the hypotheses and symbols. In words, what does this mean? This means the drug and the placebo have the same effect, or both groups develop cancer at the same rate, drug or placebo. Over here, this says the group with the drug develops cancer at a lower rate than the group with the placebo. At the end of our test, we came to the conclusion to reject this one, to reject the null hypothesis that the drug has no different effect than the placebo. And so here we come to the conclusion that indeed those taking the drug develop cancer at a lower rate than those taking the placebo. And that's what I'm writing here. We have evidence that I could write that those taking the drug develop cancer at a lower rate than those taking the placebo. Or simply I write, we have evidence that the drug does reduce the proportion of men developing cancer. Yes?
The further it is away from 0, and the more you reject it. I'm sorry.
Yes. If your test statistic is very far away from 0, you will reject the null hypothesis. You are more likely to reject the null hypothesis as your test statistic gets farther away from 0.
That's why I didn't understand that. That is very close to 0, am I right?
This is not my test statistic, this is my p-value. So my test statistic was -5, which is far away. That results in a small p-value. If your p-value is small, you reject. If your p-value is large, you do not reject. Okay. going to do problem 2 now. Problem 2 is very similar to a homework problem in chapter 9, if not exactly the same. Okay, so this is very similar to chapter 9, problem 26 in the homework. Okay, so chapter 9:26, and it says a random sample of 15 women. We took women's resting pulse rates from the National Health and Nutrition Examination Survey, showing a mean of 73.5 beats per minute and a standard deviation of 17.1. Assume that pulse rates are normally distributed. So we have a sample of 15 women. The mean is 73.5 beats per minute, and the standard deviation is 17.1. And we want to make a 95% confidence interval based on this data.
Is that it, Professor? 15?
15 women. So very similar to chapter 9, problem 26. We're making a 95% confidence interval. So the formula for a 95% confidence interval is this: x bar plus or minus t star times s over the square root of n. So I'm just going to plug in the values that I have. My mean, 73.5, that is x bar. Plus or minus, we're going to have to go to the table to find t star. S is 17.1, and I'm dividing by the square root of n, which is 15. When I look up t star in the table, how do I do this?
And I'm minus 1.
I'm going to use degrees of freedom equal to n minus 1. So how many degrees of freedom do I have?
14.
14 degrees of freedom. And I go to the column that says confidence level 95%. So when I look that up, the t star that I use is 2.145. And so I just plug that into my equation. So I have 73.5 plus or minus 9.47. And so on the low end I have 64.03. And on the high end I go to 72.97. So this This is my 95% confidence interval. Based on this interval, part B, do we have evidence that the mean heart rate of all women is different from 68 beats per minute?
No.
We have a question, yes?
Hi, sorry, is it supposed to be 64 to 82?
I'm sorry, 82, that's correct. Sorry, I apologize. No, that's a good observation. Okay, so part B asks, do we have evidence that the mean heart rate of all women is different from 68 beats per minute?
All women, that's the most important there.
So part B says, do we have evidence that the mean heart rate of all women is different from 68 beats per minute? And our answer is
No.
no, because 68 is inside the interval. Okay, so the answer is no. Part B is asking about all women.
Oh, it's not part A.
That's part B. Part C says, based on the interval you made, do you have evidence that the mean heart rate of your sample of women is different from 68? And the answer there is yes. Why is the answer to part C different?
Because it lands in between our interval?
Okay, so C asks for your sample. All right, you guys.
It's exactly 68, right?
So what we know is that the mean of my sample is 73.5. So the mean of the sample is 73.5. So do I know that the mean of my sample is different from 68? The answer is yes. 68 is not 73.5. And that's it. Okay. So I know that a confidence interval is always talking about the mean of the population, or the mean of all women. 68 is inside the interval. Yeah. .68 is in the interval, so it is a plausible value. But when we're talking about the sample, we just look at the mean of our sample, and that's not 68.
It's not in because
So the confidence interval is always about the mean of the population. So in part B, it's asking, does the interval provide evidence that the mean heart rate of all women is different from 68? So we're talking about the mean of all women. And that value 68 is within my interval. My interval goes from 64 to 82.97. 68 is between 64 and 82.97. So that means 68 is a plausible value for the mean heart rate of all women. Yeah. Do I have evidence that it's different from 68? No, I don't have evidence that it's different from 68. All right, so let's take a look at problem 3. So the problem 3 is very similar to chapter 9, problem 32. It says the mean weight of all 20-year-old women is 128 pounds. Okay? So the mean weight of all 20-year-old women is 128. Okay? We take a random sample of 40 20-year-old women. So we have 40 women. They are professional athletes, and the mean is 136 pounds, and the standard deviation of our sample is 15 pounds. So we're going to do a hypothesis test to determine if the mean weight for all 20-year-old women who are professional athletes is significantly more than 128 pounds with significance level 0.05. So part A asks, what are the hypotheses? So in this case, we have a numeric variable. We're looking at the weight of someone, and we have one sample. So my hypothesis is going to be that mu is equal to some number, and the alternative is that mu is
Greater than.
now we're asking greater than. Okay, and so we're asking, do we have evidence that the mean weight of women who are professional athletes is more than 128 pounds? So the alternative is going to be that mu is more than 128, and the null is going to be that mu is equal to 128. What is the standard error? The standard error is s over the square root of n. So we're going to use 15 divided by, 15 divided by the square root of 40. So I get a standard error of 2.372. My test statistic is going to be x bar minus the number and the null hypothesis divided by the standard error. So my mean for the sample is 136 minus the number and the null hypothesis, which is 128, divided by 2.372. And I get 3.373. That is my test statistic. Part D asks for our p-value. So to get this, I'm going to go to the t-table. We look up test statistic in the t-table. Whenever I'm dealing with numeric variables, we're using the t-table. How many degrees of freedom do I have?
19. Oh no, 39. So you look at 30.
So degrees of freedom is 40 minus 1. I have 39 degrees of freedom. But 39 is not listed in the table, so we use 30 degrees of freedom. So using 30 degrees of freedom, I'm going to look up my test statistic 3.373. So the numbers, relevant numbers I see are 2.750 and 3.385. So at 3.385, my tail area is 0.001, and at 2.750, my tail area is 0.005. 3.373 is in between 2.750 and 3.385. So my tail area is going to be in between 0.001 and 0.005. So my p-value, is my p-value equal to the tail area, or do I have to double it?
You don't double it.
I do not double because I have a one-tailed test as indicated by my alternative hypothesis. So my p-value is between 0.001 and 0.005. So that is my p-value. Would I reject the null hypothesis or not reject the null hypothesis? Which is part E. So my p-value is, if I'm using alpha equal to 0.05, my p-value is definitely less than alpha. Okay? Alpha is 5% and I'm getting 0.005. So I would reject the null hypothesis. And what does this mean when I reject the null hypothesis? We have evidence of what? We have evidence that the mean weight of professional athletes, mean weight of women who are professional athletes
Are higher.
is more than the mean weight of non-athletes. Is that okay? Good. Yes.
Problems like this will be relevant as well, you ever find something.
Yes, so the final exam will be quite similar to this quiz in that I will present some kind of problem and I will ask maybe 3 or 4 questions related to that. Asking things like, what would the hypotheses be in this test? Or what would your test statistic be? What would the conclusion be?
It's similar to our practice in that
Very-
we
very-
have like one little section for.
It's very similar to the practice final. Yes. Yes.
So, for example, for the final, you'll have like a subheader for each section. You'll have one question, and each one of those multiple choice questions will be a small part of the answer for the full question, right? You know what I'm saying? Like, you'll have like a giant questions, and you'll be like, multiple choice questions 13 through 18
Yes.
are for this.
Yes, so it'll be very similar to the practice final exam. Okay? I'll have a paragraph with information, and I'll have 4 or 5 questions, around 4 questions per thing related to that. Okay, let me cover the topics from chapter 12. The homework this week, I will not be collecting, okay? So you don't have any paper to turn in related to chapter 12. Just look at the problems that I've assigned from chapter 12. You don't have to turn in any paper next week for the final exam. Chapter 12 is just about sampling methods. So we talked about a very lightweight chapter. I'm going to teach you 4 sampling methods. One of them you already know. And all you have to do is be able to identify which sampling method is being used in a particular situation. So your 4 sampling methods are simple random sampling, stratified sampling, cluster sampling, and systematic sampling.